Welcome back, everyone, to the deep dive. Today, we're diving into something uh, pretty wild, a new language model architecture that scales its reasoning power in a way that kind of mirrors how we think.
Yeah, it's pretty fascinating. The model's called Huygen-0125, and it's designed to solve problems with different levels of thought. You know, like some tasks need just a quick analysis, while others need a much deeper, more iterative approach before it can even come up with an answer.
I see what you're getting at. Like when we're faced with a challenge, sometimes the answer just pops into our head,
hmm
but other times we need to really think it over, mull things over internally, and then boom, the solution appears.
Exactly. And that's what this model is all about. It's described in this research paper titled Scaling Up Test Time Compute with Latent Reasoning, a recurrent depth approach.
So most language models we've talked about before, they increase their reasoning power by generating more tokens. Like they're thinking out loud step by step. But this one's different, right?
Right? Huygen. It's actually named after the thought raven in Norse mythology. And it thinks internally, using a special recurrent block that can repeat as many times as needed, kind of like it's unfolding its wings at test time to reveal these deeper layers of reasoning.
I like that image. So this recurrent block is what lets it scale its thinking power without needing those extra tokens.
Precisely. It lets the model go beyond the surface level and really dig into the problem going through that thinking process over and over until it gets to a solution.
And I heard this model was trained on a massive data set using some pretty serious computing power.
Oh, yeah. They use powerful AMD Frontier supercomputers. It's possibly the largest training run we've seen on an AMD cluster. And get this, the model was trained on 800 billion tokens. That's a lot of data.
It's mind-boggling. So what are the big advantages of this way of reasoning? How is it different from that chain of thought prompting that's been so popular?
Well, a major advantage is that it doesn't need any special training data. Those chain of thought models, they have to be taught how to think step by step. But Huygen, it learns from regular text data, like we learn from reading books and just taking in information naturally.
So it's more adaptable. It doesn't need that extra coaching during training.
Yeah, and because of that, it's also much better with memory. Unlike those chain of thought models that need super long context windows, Huygen can handle information in smaller chunks and still do its deep reasoning.
So smaller model, less memory, but potentially more thinking power. That sounds amazing. But how does it actually work? Can you walk us through the architecture?
Picture a song with an intro, a verse that repeats, and an outro. That's kind of like Huygen's structure. It's got a prelude that embeds the input, a recurrent block that repeats for deeper reasoning, and a coda to produce the output.
So the verse is like the main reasoning process, and it can repeat as many times as needed depending on how hard the problem is.
You got it. And this repetition, this ability to think deeper, that's what makes this model so special. It leads to some really cool capabilities.
I'm definitely curious about those capabilities. Now, I understand there was some roadblocks during training, but they also had some breakthroughs. Can you tell us more about that process? What were some of the challenges and how did they overcome them?
Yeah, training a model as complex as Huygen, it definitely had its challenges.
Mm.
Early on, the researchers ran into something called model collapse.
Model collapse. That sounds a little scary. What does that even mean?
Well, basically, the model's output just became nonsense. It started predicting the same thing for every input,
Yeah.
almost like it forgot everything it had learned.
So instead of giving us all these different insightful outputs, it just got stuck repeating itself. That must have been frustrating for the researchers. How'd they figure out what was going wrong and fix it?
It was a real head-scratcher. They found out that this collapse was happening because of how the model's internal representations, its thoughts, were changing during training. All those constant updates to its understanding, combined with the recurrent block going over and over, it caused things to get mixed up, like trying to juggle too many ideas at once, and they all blur together.
So they needed to find a way to keep those thoughts organized as the model learned.
Exactly. They had to make sure the information flowed smoothly through the model during training to prevent that mixing up. And their big breakthrough came when they realized that the problem was actually a combination of the model's architecture and how they were setting up its initial parameters, those settings that control how it learns.
Also, like fine-tuning the learning process itself.
Yeah, by using a specific normalization technique and a new way of initializing those parameters, they were able to stabilize the whole training process and prevent that collapse from happening.
It's amazing how those little tweaks can make such a big difference. Once they got that sorted, were they able to unleash Huygens' full potential and see how it stacked up against other models?
They were, and the results were pretty impressive, especially considering Huygen is actually smaller than some of the big models out there.
Yeah.
Remember, it's got 3.5 billion parameters, which is tiny compared to some that have hundreds of billions.
Right, but it seems like science isn't everything with these language models. So what kind of tests did they use to gauge Hujin's reasoning skills?
They focused on tasks that really need deeper thought, like solving math problems and writing code.
Yeah.
Things where just memorizing stuff wouldn't cut it. They wanted to see how well Hugin could actually reason, not just how much it could remember.
So it was all about putting its thinking cap on. How did it perform? Was it able to keep up with those bigger models?
It did more than keep up. It actually blew them out of the water in those areas, outperforming a lot of general-purpose models. And it looks like its success comes down to how it uses its thinking power strategically. Instead of wasting time on simple stuff, it focuses its energy on the more complex parts, like a chess grandmaster who can size up the board in seconds and zero in on the most important moves.
So it knows when to really put in the effort. That's pretty remarkable. To really see the impact of this recurrent block, did they compare Hugin to a model without it?
They did. They actually created a non-recurrent twin, basically a version of the model without that repeating verse in its architecture, just to see how much of Hugin's success came from its ability to think deeper.
Clever way to test it. So what happened?
The difference was night and day. Hugin, the one with the recurrent block, totally outshined its non-recurrent twin, especially on those tough reasoning tasks. It was clear proof that that iterative thinking process is what gives Hugin its edge.
So this architecture is really pushing the limits of what language models can do. And the fact that Hugin kept getting better throughout training, especially with those math and code problems, suggests there's even more to discover.
Absolutely. It's like we've given it the tools to learn and grow, and it keeps showing us new depth to its abilities. But there's more to it than that. Remember those zero-shot abilities we talked about?
Right, the whole it can do things it wasn't specifically trained to do thing, it still sounds kind of magical to me. Can you give us some examples of what those zero-shot abilities look like in action?
Sure. Let's take adaptive compute, for example. Hugin can actually figure out how much thinking or how many times it needs to run through that recurrent block for each prediction. It's almost like it has its own internal effort meter adjusting its thinking power as it goes.
So for easy tasks, it doesn't overthink things. But for the hard ones, it knows to kick things into high gear and use more brain power. It's amazing how it adapts to the challenge. What are some other examples of these zero-shot capabilities?
Another cool one is KV cache sharing. This lets the model reuse information it's already calculated, which saves time and resources. It's like having a perfectly organized filing system, so you can find exactly what you need instantly.
I like that analogy. It's learning to be super efficient. And then there's that continuous chain of thought ability we mentioned earlier. Can you explain that a bit more?
Of course. So this lets Hugin remember and build on its previous thoughts when it's working on new problems. Kind of like how we use context in conversations or draw on our past experiences when we're making decisions.
So it's not just about solving one problem at a time. It's about understanding how they're all connected and building a bigger picture, almost like it's developing its own internal model of how things work.
You're exactly right.
Yeah.
And that leads us to probably the most mind-blowing part of this research, visualizing Hugin's thoughts in the latent space.
Yeah. You mentioned orbits and sliders and stuff like that. I'm really curious to hear more about what those look like and what they tell us about how Hugin thinks. Can you break that down for us?
Okay, so we're talking about visualizing Hugin's thoughts. And it does sound super complex, almost like something out of science fiction. But the researchers figured out a way to actually see it happening.
So how'd they do it?
They used a technique called PCA to create a visual representation of how the model's internal representations, its thoughts, were changing over all those iterations. It's like they found a way to peek inside the model's mind and watch its thoughts taking shape.
So they could actually see these abstract ideas moving around in the latent space. What did those visualizations look like?
Imagine a map of the stars tracking how they move. They saw different patterns. Some tokens would just converge to a fixed point.
So it's like the model has a solid understanding of that concept. It doesn't need to think about it anymore.
Exactly. And then there were other tokens that moved in these circular or elliptical paths, like they were orbiting around an idea, exploring it from all sides.
So instead of just settling on one definition, it keeps circling around the concept, getting a more complete understanding.
Yeah, and then some tokens would slide in specific directions.
Yeah.
Like their understanding was gradually evolving and becoming more refined.
It's like watching the model learn in real time, seeing how its thought process works as it grapples with these complex ideas.
It really is a fascinating glimpse into how this model works. And it challenges how we traditionally think about language models, learning, and reasoning. It's not just input and output anymore. There's a whole world of thought happening in that latent space.
This is all pretty mind-blowing, but let's bring this back to our listener who might be wondering how all this impacts their lives. If Hubin is still in its early stages, what does this research mean for them?
Great question. And here's the takeaway. These models, they have the potential to totally revolutionize so many aspects of our lives. Imagine a world where AI can help us solve some of our biggest challenges, like climate change or finding cures for diseases.
That sounds like a future we should all be working towards. But what would those AI solutions look like in practice?
Think about personalized AI assistants that really understand your needs and what you like. They could adapt to your lifestyle. Or imagine educational tools that tailor themselves to your learning style, making learning more fun and effective.
It's like having an AI companion designed just for you for everything you do. It's not just about solving big problems or improving our personal lives, though, right? Could these models change entire industries?
Absolutely. Feels like scientific research and medical diagnosis could be completely transformed. AI could analyze tons of data and find patterns that humans might miss, leading to huge breakthroughs.
And what about creative fields like art music writing? Could these models become tools for artistic expression?
I think so. Imagine AI that could help us write better stories, compose incredible music, or create amazing art. It could push the boundaries of human creativity even further.
It's exciting and a little scary to think about all the possibilities. But with all this potential comes responsibility. How can we make sure these powerful AI models are developed and used ethically?
That's the big question, and one that researchers and developers are thinking about a lot. As we keep pushing the limits of AI, we have to prioritize ethics, making sure it's developed and used transparently, fairly, and responsibly.
So it's about finding that balance between innovation and responsibility, making sure these powerful tools are used for good.
Exactly. And that's why research like this is so important. It's not just about building smarter AI, it's about understanding how it'll impact society and making sure it benefits everyone.
Well, I think our listeners have a lot to think about after today's deep dive. This has been an amazing look into the world of recurrent depth models and how they could shape the future.
It's been great exploring this groundbreaking research with you, and I hope everyone listening is as amazed and excited as we are about the possibilities that lie ahead as we keep unlocking the secrets of artificial intelligence.
Thanks for joining us on this deep dive into the future of AI. Until next time, keep exploring, keep learning, and keep diving deep.